All right, we are now live. So I promised I would do a better picture of a cycloid with GeoGebra. And so here is my circle rolling,
which is so cool,
with the point A on there. And that is what a cycloid is.
So cool.
So I'm just going to give you a couple of facts about a cycloid. We'll do a couple of other parameterizations, and then we're going to do a bunch of calculus on them. So the questions we're going to answer is, how do you do slope with parameterizations? How do you do area? How do you do arc length? No, start right now. So this is one really cool thing about GeoGebra. You can do animate off. Stop. But I want to turn the animation off now. Yeah, so you can, with GeoGebra, you can either have the animate run automatically, or you can just make it run manually. Did I tell you guys about my front door? No, so this is cool. So I like math. You guys may have gotten the point that I like math. So when I was building my house, I decided to incorporate as many cool math things as I could. So one thing I decided to do was, I have all kinds of arches in my house. So I decided to make, with a friend of mine, a cycloidal arch in my house. And so I did it in the front door. And so we cut a piece of plywood in a circle with a 1 foot diameter. And then we drilled a little hole in the top to put a pen in. And then we rolled that circle on another piece of plywood on a straight line. And it traced out a cycloid like you're seeing here. And we used that as a pattern for my door. Now here's the cool thing.
What does your door look like?
It's pretty cool. I'll show you a picture later.
Please do.
And here's the cool thing though. If I have a circle with a 1 foot diameter, what is its circumference?
Oh wait.
What's that again?
Now here I have a circle with a 1 foot radius.
Oh, so it would be 1 pi.
Yeah, if I have a circle with a 1 foot diameter, then if it rolls once, it covers its circumference, which is pi. So my door is pi feet wide. So every time I walk in my front door, I get to walk through pi.
So the door never really has an end.
Well, its decimal goes on forever without repeating to the rest of my construction and cutting abilities. Yes.
Why couldn't it be EY?
Well, you know, I did incorporate E in other places in my house.
Did you really?
I did, along with Fibonacci numbers and the golden ratio.
You did?
Yeah.
Oh my gosh.
I did a tiling in my kitchen floor that is a compass, and one part of the compass points magnetic north and the other points true north.
I really want to go to your house.
I
do.
Well, maybe we'll have a calculus party at the end of the quarter at my house, and I can show you the cool math. Okay, let's do some cool math now. So
now I have a reason to pass this class, so I can see all. We can go to your house and see all of these cool math things.
Okay, so we're going to play with, again, parameterizations.
How is this stuff?
Are you a piece of paper right now?
Yeah.
I didn't know if I was still holding on enough.
Okay. Should be
So I mentioned earlier, there are some curves that live only as parameterizations. And other times we go back and forth between what I call parameterizations and Cartesian functions. So we're just going to take a look at those two.
Yes. It's a mouthful. Like, it's a serious effort.
So an example of a Cartesian function, y equals x squared. Y equals the square root of 1 minus x squared. Y equals the sine of x. These are all what we call Cartesian functions. Y is written as a function of x. Okay, so that's the big deal.
That's all it takes.
Y equals f of x. That's what I'm referring to as a Cartesian function. The traditional things you've been looking at for most of your algebraic life. What's that? You need graph paper?
Graph paper.
Yeah. And you saying you want some or you just say?
No, I said, is that why?
Yeah.
That's why.
Yeah. Now, we're putting a little twist on this with parameterization. So a parameter is just some other variable. Okay? That variable could be totally meaningless. It could be time. It could be an angle. There's lots of things it could be. So the difference between parameterized functions is that we put some other variable in control. So for example, we looked at the other day, x equals cosine of t, y equals sine of t. Now I'm still considering a point xy in the Cartesian plane. I'm just using another value t to help me find those. T could be time in seconds. In this case, we were letting t be an angle measured off the positive x-axis. This was the first problem we did the other day. And we calculated that if t was equal to 0, then we ended up with the point 1, 0. And when t was equal to pi, pi over 2, then we ended up with the point 0, 1. And somewhere in between here, when t was equal to pi over 4, we ended up with the point square root of 2 over 2, comma, square root of 2 over 2. And a quarter circle emerged when we did that. And we could keep doing that. We could pick another value for t. But one thing you'll notice is when you do that, when you go from point to point and you watch what t is doing, what the parameters do are trace out the curve. So one thing we can do with parameterizations is we can trace curves. I could have easily done this circle a different way. I could say just use the equation x squared plus y squared equals 1. Start finding points. So this combination of equations with the parameter t is another way to draw a circle. Okay? And the added benefit I think it has is not only do you draw the circle, but this particular selection of equations forces me to start drawing at this point when t is 0 and go around counterclockwise. Is it possible to draw the circle starting at a different point, to go in a different direction?
Yes.
The answer is yes. You just tweak your parameterization to do that. Okay, so we're just going to have a little fun with parameterizations. So let's see. Here's what we're going to do. We're just going to do one and then see what happens. Suppose instead I let x equal the sine of t. Oops. I'm supposed to be t there. And y is going to be the cosine of t. Will that result in the same exact curve that I had before? The answer is yes and no. It'll trace the same shape, but it'll do it differently. Do you all know how to put your calculator in parameterization mode?
Yes,
Okay.
taught me.
It's in the mode menu. For some reason I wanted to say bless you, but I don't think you usually say that when you pick up.
I don't know.
I kind of felt like I was ready to say bless you too.
All right. So if I go to the mode menu on my TI, it's in what's called function mode. Next to that is PAR, that's parametric mode.
Whoa, what is the one we haven't learned about yet?
Polar or sequence?
Oh,
Polar.
We're going to do polar next, after we do parametric.
We learned about all sorts of modes on my
We are,
calculator.
we're going to do all kinds of stuff. So put your calculator in parametric mode, and then from parametric mode, go back to the y equals screen. And then this gives you a way to type some equation for x and an equation for y separately. One thing you'll notice is that the x key turns into a t key.
Yeah.
The standard parameter in GeoGebra and this thing, TI.
Wait a
is
minute.
T.
So is the theta for polar mode?
Correct. Theta is for polar mode. Yes.
Look how cute that is.
And it's contagious, isn't it? Cute now. Cosine. So we're switching what sine and cosine do, and we're going to see what happens. Then you got to pick a window. Now the window is a little trickier because not only do you have to say where to look for x and y, but you got to tell the calculator what values of t to use. So So what value should t be to do a complete cycle for sine or cosine?
0 to 5.
0 to 2 pi, yeah. So I'm going to go from 0 to 2 pi for t min, t max.
It's literally mine's already
There's a
in.
graph on that one.
We'll get there. Hang on. Let me catch up. So let me see. Where the hell is 2 pi? 2 pi. There we go. The step is how often to plot points based on t. Mine is set to 0.1. What's yours set to?
0.1300996 blah 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 blah.
7.5.
0.6.
I have no idea what that means. But so it doesn't really matter. But if you pick your t step to be too big, what happens is something like this.
Oh, well, that's not what I want.
Okay, maybe that's why mine's fucking.
Right. So weird things. So if I was trying to graph a circle with a t step that's too big, something weird like that's going to happen. If I make t too small, it's going to get stuck trying to graph points and do so very slowly. So it's kind of an art to pick a value for t that's not too big and not too small.
So 0.1.
Yeah.
So I'm going to go for 0.1. I have no idea if that's good enough at the
My
moment.
calculator's not like 20
Actually, I do know if it's
5
good.
or 50.
It didn't like 5 or
Okay,
50?
so
Okay.
why is that why mine's doing that?
So then I have to pick x and y. Now this is the unit circle. I think I'm still graphing. I think I'm just changing the way it graphs. So I'm going to go from negative 1.5.
We don't farm like God.
Oops.
Oh. It's like one little line.
To
That's all
1.5
mine's doing.
in x and y.
Yeah,
Again,
it's working on
it
it.
just looks like a little dash.
The 1.01. It's growing very, very slowly.
Yeah.
Yeah, mine's up.
Yeah, that's
Yeah, so you could potentially kill your calculator, drain your battery if you make t too small.
It's still trying.
7.
Oh, mine's having a
So
graphing
0.01
issue.
is a bad decision.
Okay.
Jeff, what did you
What else?
0.01 is a bad machine.
Mine looks like this.
Yeah.
It doesn't look great.
Hey, 0.1.
So there's
No,
mine.
it's going slowly.
I'll graph it again just to see it.
How do I do it?
Okay, yeah, so what?
Why does yours
That's
go so
interesting.
fast? How did yours
Just use a
go?
computer, so.
Oh, yours is in degree mode. That's
Oh.
Oh. Is that what we're
You
doing?
definitely want to be in radio. Oh, no, you're in radio mode.
Oh,
That's
wait.
not wrong because of physics again.
Oh, okay, I switched to radian now. Oh,
Okay.
that worked so much better, guys.
Go! Circle made.
What did you do?
Oh, it's because it's set to draw that line.
Oh.
So we'll just arrow over and set it to draw a skinny line.
Okay.
That's a
Mine just keeps going
Okay, so
around
you
and
just
around
take t
and
go far
around.
enough. So
Whoa,
we'll
how do you
cycle
make it
circle
flat?
to
I want to make it dotted.
How do you make it skinny?
Cycle like
Where are
this.
we?
Look at that, dotted. It's dotted.
How do I
Okay.
stop mine from going around and around and around?
Oh, that's
So-
good.
I don't know why one
So I'm just going to show you some more pitfalls. Notice mine didn't quite finish. There's a kind of little bitty gap in mine. I don't know if you can see it there.
I was doing this. And it goes 7.
Oh.
Now, mine doesn't look like a circle. What the heck's wrong with that?
Oh, well, I feel like.
Is this how you change it?
Your window is not equal?
Yeah, my x and y are not set proportionally. So I have 1.5 longer than it is tall on this particular window.
How do you do
And
that?
mine
So cool.
has a little gap.
Look at this. 40 kids. How do you do that?
Oh, this is way too much fun.
Look at that.
Yeah.
So,
She made it like a ball, like rotate in the circle, like around
oh
it.
yeah, that's fun, huh?
How
I'll
do
show you how to
you
do
do
that.
that?
Okay, so I believe this is what happened on mine. So right here, t is equal to, let's see, that's 3 pi over 2 at this particular point.
My mind.
I
Sorry. I'm
Here,
listening.
t is equal to pi.
That was way too much. for me.
So we got it to roll counterclockwise.
So wait, you got a gap? I didn't get a gap.
Why did I get a gap? If
It's
you look at
because
my
of the T
window,
maximum.
yeah. I made my window exactly 2, or just, it's almost 2 pi, and it couldn't quite get that last point.
That was.
So if instead I made it, I rounded that up a little bit to like 6.29,
That was so cool.
6.3-ish, then it should complete it. Okay, so it closed the gap that time. Okay. So, pitfalls are if you choose a t-step that's too big. Like if I made my t-step 1, I get a polygon. if I make my t step 1 and I let t keep going around and around, like I make t like, I don't know, 100?
T maximum?
T max,
Yeah.
sorry.
I set mine.
Then
like
I get some
360
weird
originally.
stuff.
It took forever.
Uh-huh.
That looks like a spirograph.
That's what Courtney's look like at first.
Yeah.
And she finished it.
Okay, so you got to be a little bit cautious, and often
Ooh.
your first shot at T min, T max, and T step is not going to be right, but you got to mess around.
This is officially my new favorite thing to play with.
Okay, so I'm going to go up to T equals. I'm going to go
Give someone a graphic calculator.
up to 4 pi, and I'm going to step by 0.1. Seemed reasonable to me. Let's see, what else do I want to do?
Like, is it-
Here's another cute thing you can do. If you arrow to the right of X, you can change how it graphs it. And so I'm just going to hit Enter until it shows me graphing the bouncing ball.
That was so cool.
And so now if I hit graph, it'll show a little ball running around tracing the curve.
Ooh, see, that's what I mine did that too.
Courtney did that. It made my whole entire day. Why do I have math on my birthday? Math always makes me so happy.
So you can come by tomorrow. We can do it.
And English makes me so depressed.
Mine disappears after 1 minute.
Okay, I set my T max to be 4 pi. So I made it do 2 revolutions.
That is so
Okay. So this one went counterclockwise. Any thoughts on what I could do to start at the same point, the point 0, 1, but make it go, let's see, that went clockwise. I want it to go the other way.
Switch the two-sided function.
Well, that will also make it start at a different point. We're just going to play around with how to change the parameterization. Yeah, make t negative.
I was, yeah, you make it negative.
So if you make t negative, now with the cosine, that's not going to matter because the cosines will call it an even function. It kills negatives.
Yeah.
It just swallows them whole. But I'm going to do it for both of them anyway.
I made a better circle anyways.
So negative t.
Hey, mine's blue. I mean, mine.
What? You might. Oh, right. You have a fancy.
Oh, you have a newer one? Negative t. So now if I graph it,
Yeah.
Well, because I saw you show it to Jeff.
so here's some other things we can do. We could shift t. How do you shift something to the left or right, backward or forward? Replace x with a number. Yeah, you add to it. Like you could replace x with x plus 1 or x minus 1.
I'll make it worse.
Why is it doing
So
that?
try doing a t minus 1. See what happens.
Why is this
On
bump
both of them?
Hang on.
Oh, you want to switch direction? You want to shift it?
You pick.
Hard to
See if it does what
very-
you think. Yeah.
Hey, go back to that. Why did you do that?
No, it started over there.
That's t minus 1.
Wait a minute.
Sine t minus 1.
Oh, we did change cosine.
I wonder if I do
Do
minus
this.
0.5.
Nice circle, nice.
That did not do it all.
So it's getting lumpy.
Literally
It's
like
just
a
the
desk toy.
calculator's
Oh,
crappy
did you
resolution. It's the closest it can get to the actual point.
Why did you
It's all
do
right
that?
on the other
If-
side.
well, if you change your t step, it'll change that. It'll
Mine
put
did
points in
not look
slightly
like
different
that.
places.
Are you sure?
Huh.
Why didn't it look like that? Why didn't mine look like that?
Mine looked like I flipped it on the z-axis.
That's because I didn't put it into cosine, I just put it into sine.
Oh.
I like this better. It just looks cooler.
I'm pretty sure this is my new favorite toy. Really?
Yeah,
It's like
I know, me too.
Wait till we get to polar. Polar's pretty rough. Yeah, so if I replace both t's with t minus
It
1,
just starts.
then I've just shifted time. Okay,
Shifted.
I just shifted time, yes. I had it start graphing 1 second earlier. And 1 second earlier, it's going to be right over here. If I wanted to start right there,
Wait,
what
so
would I
it'd be
shift
like
by?
1 was 1 second?
What's that?
So 1 was like 1 second?
The maximum?
So 1 second now happens at the top where it used to be 0.
Okay.
That's what the shift
Oh,
is.
right, because T is time.
Yeah, because t is time. So if I shifted it by pi over 2,
It's the t step though, or the t max.
all I'm doing is replacing t here in my.
Oh, there.
Yeah, so I'm doing a substitution. I'm not messing around with the t min, t max. Although that will make it look like it's starting in a different place. So what I did is just a substitution. Instead, I graphed x equals the cosine of t minus 1 and y equals the sine. Oh no, wait, I got this backwards.
This is so fancy.
I want x sine and y cosine. Sine and cosine. of t minus 1. So since this thing was graphing clockwise, that gave me a shift essentially back. So it starts sooner, back 1 unit.
Yours worked with the
1 unit of time.
inside the parentheses or something?
Yeah.
Mine did. It just looked like I flipped on the z-axis and moved it outside parentheses to move on that axis.
Let me see yours.
What?
I made a figure 8!
This is what I had to do there. It's very cool.
I made a figure 8!
Do this though.
That is so fun.
Here we go.
Okay. How do you?
T-max, I think pi plus
Okay.
0.0.
I bet you did amazing.
Oh, no, you gotta keep this there.
We're learning how to plan our
Yeah,
calculators.
Otherwise you do
No,
years.
it's gonna be
No,
It's
yeah,
like-
that's
it was
what
like-
you do.
Okay.
And then look like it's over
The
the
question
z-axis.
for you did that paper? I'm not
So
sure if you
that's
want
should
actually.
play.
I thought I at least did everything that I could have done, so if you guys feel on it.
Here we go, your test.
Oh, just more. It was only like 5 off plus all the.
Gary's only 3 columns, like 28 letters each.
Like something else.
Okay, bye.
Okay, so, when I look at this question right here, when I look at this graph, I don't see a circle. Now that's because my calculator is distorting. To fix the distortion, I could go zoom and choose the square option, number 5.
What?
And it makes 1 unit for x equal to 1 unit for y, and then it looks like a circle. But aren't there ellipses that look very circular?
Courtney's doing all sorts of fun stuff. It looks like a pair of legs.
So I just want to prove that
Ooh.
this particular parameterization right there is indeed a circle. So let me get this out of the way. Okay, so here's how I'm going to prove it. What formulas do you know that relate sine and cosine to each other?
Tangent.
Tangent, that's one. What else?
Cotangent.
Cotangent.
Cosine squared plus 1? No.
Oh, Joan,
How about-
isn't that 1 times e squared plus 1 equals 0, or minus 1 equals 0?
I was thinking more simply than that. Just I know that sine squared
Plus cosine squared.
plus cosine squared equals 1.
Oh.
Yeah.
Well, at least
That was too general a question. My apologies.
I mean,
That was too
whatever.
general.
What was your
So
question? Well, I did say cosine.
can you give me an equation that links sine and cosine together?
Oh, I didn't know you meant it like that.
Yeah, that's okay. It was a stupid question.
Trig identities.
Yeah, trig identities. Let me.
I immediately thought of that as trig identities, but then I was like, I don't think that's an equation.
Yeah, it is. It's a trig identity equation. And what is sine equal to here?
Oh, wait, this should be in pink.
X, right? So I can replace sine with x, which means I have x squared.
Oh, yeah.
I can replace cosine with y here, which means I have plus y squared.
Oh, that's a.
So to shift a parametric set of equations into what I'm calling a Cartesian function, or a Cartesian equation, you have to have some way to re-relate.
That was cool.
Is that always possible? No, that's not always possible. So what I've done is I've just rewritten it this way, and I could solve that for y. Y equals plus or minus the square root of 1 minus x squared, plus being the top half of the unit circle, the minus being the bottom half. Yes?
So, because they're both equal to 1, could you say that sine squared t plus cosine squared t is equal to x squared plus y squared?
Yes, in this case you can. Yeah. So these are equal
That was fun.
in
Okay.
this circumstance, yes. Because we made this assignment up above. Only because of that assignment up above.
Right. X equals like 27.
So I'm gonna give you another situation, and we're gonna see if we can figure out what it is.
That's fun.
So suppose I gave you that x was equal to twice the sine of t
This is just
minus 1, and y is equal to 4 times the cosine of t. Let's graph that parameterization and take a look at it, and then we'll see if we can prove that the shape is what we think it is. Sorry. Oops. And make sure you use parentheses properly.
What did you say? Why was 4 cosine?
4 cosine t?
Is there a
I meant
minus
X,
one?
right?
I
It's
didn't
2 sine
see
t
that.
minus
Yeah, there's a -1 after the sign.
Oh, that's too big. Not fit in my
I'll have to fix that.
window. So, what should my minimum?
So we clearly need to adjust the
That's what mine
window.
looked like. I felt like that was wrong.
Yeah.
Oh, interesting.
Maybe if it would stop loading.
Maybe I do like 5.5.
Okay. So if you hit trace, you'll notice you'll be given what point you're at for t, x, and y. And when you trace here, you're tracing according to t, which happens to change x and y. If you just type a number like 4, it assumes you mean t equals 4, and will tell you where x and y are. So try to adjust your window till you can see the whole thing.
Can I do a bubble?
How is putting this anyway?
Yeah, it's different.
Wait a minute, what am I doing right now? My Y. My Y max should be like 7. My Y min should be like 5. Okay, that's not what I wanted it to do. Whoa.
Okay, so I went from -5 to 5 for both x and y, and I can see the whole thing. And then the question is this a circle or an ellipse? Probably an ellipse. Okay, so just to double check, I'm going to go zoom square. And that will adjust it so 1 unit in the x direction is the same as 1 unit in the y direction. And that does not look circular, it looks elliptical. So now the question is, which ellipse is this? Well, it's this ellipse. Can we guess what the major and minor axes are?
How do you do that?
So we're going to play around. What relationship do we know that draws cosine and sine together?
Sine squared x
Yeah.
plus, sine squared.
We know that sine squared of t plus cosine squared of t equals 1. So what we're going to have to do is solve each of these equations for sine and cosine respectively. So I'm going to do the y one because it's easier. If I solve for cosine, I get cosine of t equals y over 4. So that means where I used to see the cosine, I can replace it with y over 4, and then I can square it. Similarly here, to solve this for sine, I would have to add 1 to the other side, and then divide by 2.
Yeah.
So that's going to give me that the sine of t is equal to x plus 1 over 2. So now I can replace x plus 1 over 2 with the sine, and the whole thing has to be squared.
Just
So I'm just going to clean it up a little bit. This gives me x plus 1 squared over 2 squared, which is 4, and y squared over 16 equals 1. So the critical numbers here, the important numbers, the 2 here tells me, that gives me half the length of the major axis in the x direction. The 4 gives me half the length of the major axis in the y direction. And the numerators tell me that the center x value is -1 and the center y value is 0. Right, so I'm just going to draw that information out roughly in the corner here. So if I go bring myself to the point -1, 0, which is right about there, and in the x direction, I go 1, 2 units in each direction, and in the y direction, I go 4 units up and 4 units down. puts me about here, and 1, 2, 3, almost off my screen down here. This is a rough sketch of my ellipse. So apparently my ellipse has the points -1, 4 at the top there, and I can confirm that on the TI, that it indeed has that point. Now, who cares about parameterizations of known curves? Who gives a shit?
I don't know, someone who wanted to play with cracking calculators, obviously.
Courtney does. Courtney loves it.
So here's one interesting way. My brother-in-law runs a sheet metal business, and they make all kinds of stuff, right? From cases to a projector like this, to metal plates that you can do on and off switches, you name it, they make it. How on earth do we build stuff like washing machines, like cars? How does that happen? Well, it's pretty automated these days. So if I had a sheet of metal, and in that sheet of metal, I needed to carve an elliptical hole and some circular holes,
It's nice.
and maybe put some teeth in it. How do we do that kind of thing? How do the machines do that? Now, it used to be somebody very carefully traced that out by hand, got out their welding torch, very carefully cut that out.
They use CNC routers now.
And how do those things work? How do those routers work? They work with equations like this. They work with equations like this. You can program in equations that tell them how to move. Now, sometimes they're known equations like this. Otherwise, they're just very complicated sets of points, which other kinds of mathematics are used. But parameterizations tell computers how to move. From 2D routers to 3D routers to all kinds of other stuff.
I don't believe it. Good.
I don't care. But that's one use of parameterization.
Have you ever seen an engine block get built in one piece? Actually, very, very cool.
Okay.
They take this block of metal, don't cut it in any special way, strap it to this router, and it just turns it about while the tool drills at it at every angle it can, and it makes the entire block. So these things have holes in them,
That's cool.
all one piece.
You're talking about motorcycles, right? Because I've
No,
never seen that
they
for
made
car
them
blocks.
for V8s. You guys
Really?
watch it happen.
Go watch
So they're
how
not
it's
cast
made.
anymore. They are
A lot of times I build
block.
They are carved.
Yeah.
machines or whatever.
Yes, it was very cool to watch.
All right.
Never seen
Oh,
that
it's
car
big?
block. That looks interesting.
Yeah.
But,
Yeah.
I was like,
All right.
that is awesome. Makes it pretty durable.
So I need to go back to my cycloid here. Wow, I almost forgot I had allergies while I was doing that math. That's
Are
pretty
you
cool.
allergic to math?
No. The
No!
math is like an antihistamine. I felt
Your
better.
life will be over.
All right.
You would be so sad.
Finally!
If that was possible.
I don't think it's ever going to be possible.
Well, I'll tell you that maybe last year towards
Blow up the stuff
Throw
so
it
you
at
can see it.
because I've never been to sports.
So here are the equations I use to make my parameterization. And we derived my parametric curve B here the other day in class. If I let the radius of the circle that rolls be 1, then x is t minus sine t, and y is 1 minus cosine t. Okay, so write that down. We're going to play with this curve today.
Right now?
X is t minus sine t, and y is 1 minus cosine t. I'll show you
That's
some
T minus, yeah, T minus sine.
t minus sine t, 1 minus cosine t.
Oh,
Whoa.
you got it.
Job.
What were you guys doing?
Okay.
We just got not doing.
So let's draw what this curve looks like, rough sketch. That took 1 revolution of a circle, which rolls out exactly 2 pi if the circle has radius 1.
What's that?
If it has radius 1, then the highest point it reaches is 2.
Oh!
So the peak of of this particular cycloid is the point pi 2. And so draw your best looking curve in between. Oh, that sucks, but we're going with it. Here's my cycloid to the best of my ability right now.
So bad at drawing curves. Me too.
Take some practice. I didn't quite put pi in the middle, did I?
Do this.
Graph paper is helpful. Yeah, once I was so uptight about drawing a good cycloid, I actually cut a circular piece of paper and made it roll on my paper and traced the points out. Took a
That's like
while.
a lot of extra work.
I was stuck in an airport with nothing to do,
And you decided to draw a cycloid?
so I decided to draw a cycloid up with paper and pencil, and I did a pretty good job. Okay, so there's my cycloid. So I just want to do a couple of things. I want to figure out some calculus. So the easiest thing to do with calculus is a derivative. So it would be kind of cool to pick a point on this, like maybe over here at, let's say, pi over 6. I'm going to get a particular point, and I want to figure out what is the slope of this curve at the derivative.
What?
So we're going to see if we can figure that out. Other things I'd like to know is that point traces out this curve. I want to know how long this curve is. That would be fun to know. I would also like to know how much area is inside of this curve. So we're going to try to answer all three of those questions.
Whoa, that's
Integrate,
intense.
derivate.
Yeah, so we'll differentiate first, we'll find the area second, and then we'll go for arc length third. Okay? So let's see. How do we find slope?
Rise over
Rise over run, right? Calculus, rise over run, is dy over dx. Okay. Now, it turns out you can't do a substitution like we did earlier and rewrite the cycloid as a Cartesian function in that. So that means I can't take y as a derivative of x. But what I can do here, in the top one, couldn't I find dx dt?
I feel like yes, you could.
Yeah. And here I can find dy dt.
And then define them.
Yeah, and it turns out as long as that's the same t, slope ends up being dy dt over dx dt. I'm not going to prove it, we're just going to use it.
Makes sense.
That's fine with
Proof's
me.
not that bad.
It totally makes sense anyways.
And
So
what do you
let's
wanna
see.
do?
So what is dy dt? Let's see. Derivative of y with respect to t, the 1 goes away. Derivative of cosine is
That would be
negative sign, so that's going to be positive sine t. And then in the bottom, I have derivative t is 1 minus derivative of sine is the cosine.
Not quite.
So it's not quite the tangent, right? It's a little
So
off,
close, it's so
but it is
far
pretty close.
away.
So next thing I want to do is I want to know what point is that right there.
It's because it's sine, the derivative of sine, cosine is sine at the derivative of x. And the derivative of x is what we
Okay, Jeff?
Oh, I did it backwards, okay.
Oh, then it would be tangent.
Yeah.
All right, so the point, by the way, that we're going to have here, if I let x be pi over, or t be pi over 6, then I'm going to get pi over 6 minus the sine of pi over 6. The sine of pi over 6 is 1/2. And we can approximate that on a calculator. I'm going to get a calculator.
Oh,
I got a calculator.
got it.
I just plugged in pi over 6 into t here.
Oh.
Because I just picked the point pi over x when x is, sorry, I picked t to be, oh shit. I made a mistake.
Yes, you did. Bad, Gary.
Yeah, that's not the x value there. That was a mistake there. What is pi over 6 minus 1/2?
That'd be
0.02.
0.0235.
0.235.
Yeah. Well,
The zero, the point is on the other side of the zero.
0.0. Oh yeah, right. I'll make my mistake more obvious in a second. So 0.0.
So wait, since you're making a mistake, should I write this down?
This is okay. Yeah, my x value is just fine.
Okay,
My y value is going to be 1 minus the cosine of pi over 6, which is,
but you just picked pi.
I just picked pi over 6.
You could have pi over 2. You could have been
I could have done, right, I could have 5 over 6
Square
over
root of 3
4.
over 2.
Square root of 3 over 2.
500. Yes. Let's do
And what is that
500.
approximately?
1 minus square root of 3. 0.134. The mistake is that looks closer to pi over 12 or something.
Oh, yeah. Okay, so the actual point I picked is more like right about over here. I mistakenly for a moment let the x-axis be t, which is incorrect. Doesn't work that way. So anyway, this is the point I ended up picking. It's right around there is the blue point. And so I'm looking for its tangent line, which is more like that. But that's a bad sketch. We'll have GeoGebra draw it. It does a better job. So we're going to try and find that tangent line. So the good thing is I know the x value of that point, and I know the y value of that point exactly and approximately. Now we need to know the slope at that point. But we have a formula for that, don't we?
Yeah.
Yeah.
I don't think so.
We can take our derivative, dy dx, and evaluate it when t is equal to pi over 6.
Yeah.
And so that's going to give me the sine of pi over 6, which is 1/2, divided by 1 minus the cosine of pi over 6, which is 1 minus the square root of 3 over 2. And we can approximate that.
Well, we already. Oh, so we already got the answers for that equals.
Yeah, not for the fraction, though. So I'm just going to whip that out of my calculator. So I have 1/2. Oops, calculator on.
Your calculator can turn off on that thing too.
It powers down automatically after.
Is that really a real calculator?
I know. Hey, it's programmed to be just like the.
I could have taken that out of the program easily. That was hilarious.
No, that actually turned that calculator on.
Pay attention.
Square
It's not
root
really that funny,
of 3. Just ignore.
You just have a bad sense of humor.
right?
All right, so I get the slope is about almost 4, 3.73. So I'm just going to enter that into GeoGebra approximately. If you guys got those approximate numbers written down somewhere. Actually, I could do them exactly. So I'm going to use the point slope form, y minus y1, and we think y1 is what? 1 minus square root of 3 over 2?
Yes.
Oops. Is equal to the slope, and we think the slope is 1/2 divided by parentheses 1 minus the square root of 3 over 2. 2, right? And times x minus the x value. What is my x value? It is pi over 6 minus 1/2. So I can just type over those exactly how they are. So pi over 6 minus 1/2. Oops, 1/2. And if I graph that, I get my tangent line right there. I could even pinpoint, let's see. I wonder if the calculator will, or the computer will understand if I type b parentheses pi over 6. Ooh, it did. Check that out. Even plotted the right point for me. Is it possible to parameterize a line?
I feel like that is linearized.
So I'm just going to pick a different line where the numbers aren't so messy. How could you parameterize a line? So what we want to do, just a side note, look, suppose we have y equals 2x plus 3.
No.
And I want to parameterize that. And what I want is x as a function of t and y as a function of t. Easiest possible parameterization here. You ready? Let x equal t. Then y would have to be 2t plus 3.
That's much too simple.
I could make it harder.
You don't have to do that. No, it's fine. Don't worry about it. Wait a momentary minute. So, like, when we're doing whenever we were taking the integral and it had t in the function and then we put x in, were we like deparameterizing it?
When you use a dummy variable in an integral, you are using t as a parameter there, and I guess integrated in a way does deparameterize it, yes.
Pretty cool.
We could definitely say that.
Did you say giggle?
I said pretty cool.
Oh, cool.
All right, so
Wait,
slope is
that line doesn't do the negative side. Oh my God.
Oh, let's see. Jeff was not happy with that linear
T
parameterization.
minimum is 0.
Yeah,
Right.
it depends where you start at. So if I put t in there, and then I put, what was it, 2t plus 3?
Yeah.
And my window is going, I'm going from 0 to 6-ish. So if I go to graph that, it's only going to start at t equals 0, but it didn't graph the other side. So if you want to graph the other side, you have to let t go negative.
Can I do that with
I think so.
something else that I was doing?
Oh, well, that's going to change, that's going to affect your other parameterizations, right? Yeah. So I could start at -5 and hit graph, and then it will graph more of it. And here's where t equals -5 starts to form. Want to see something even freakier?
I can't do them individually.
Check this out. So sorry, Paisley, I'm going to make it a little harder.
It's okay. It's okay.
I'm going to choose a different parameterization where I'm going to let x equal the cosine of t. Now, since x is equal to the cosine of t, for y, I can just replace x with what I says it's equal to. And I say it's equal to the cosine of t. So in this case, then y would have to be twice the cosine of t plus 3. Graph that and see what happens. My claim is it will still be that same line.
Oh, I get it.
But the way it traces is going to be totally different. You can design all kinds of parameterizations.
Backwards. I must say, this is pretty handy dandy.
Dandy.
So
Like, what is yours doing?
Mine just made like a ballet slipper.
Okay, mine didn't do that.
Interesting.
Did yours make a, oh, that's supposed to be
It
different.
went down and back.
Never mind. Not a ballet slipper.
Yours does that. Mine does a straight line.
I'm going to go from 0 to 2
I
pi.
like different ones.
Watch how mine gets traced. I'm going from 0 to 2 pi.
Okay.
If I hit graph,
It was down and back up.
it graphed over itself. I thought I turned
Oh,
the
yeah,
little
mine
ball
does
turned
that.
off. So I'm going to turn the ball on and zoom in on that.
I
So let me
why.
see. There's the happy ball. I'm going to adjust my window a little bit to zoom in on that. Let's see. I'm going to let x go from, I think, -5 to 5 should be fine. And y, I'm going to go from 0 to 10.
I don't know. It just.
It doesn't look straight just because the TI was having trouble graphing the points, but it truly is a straight line. What was happening though is the calculator started graphing when t was 0. So we got whatever value leads to sine of 0, cosine of 0. And then what does the sine and cosine do? They bounce back and forth between 0 and 1.
That's weird.
So it's not going to graph all the points on this line. It's only going to graph the points associated when the cosine and cosine spit out their numbers between 0 and 1.
It's kind of
And the rate of change of those points is not linear because sine and cosine are not linear. So it's changing the speed at which those points are graphed as it's graphing them, based on the slope of sine and cosine. Which is kind of wild. So not only can you control the direction where it starts, you can control the speed at which it's graphed in different areas. So you could cleverly make it slow down in some spots and speed up in others. Pretty powerful. So we kind of know. I think it's pretty fun.
That's internet, dude.
All right, back to calculus.
Back to it.
All right. Next, we're going to try to find the area under that curve.
okay.
So I think I will
So
steal
that was
that curve from
12.
the picture. Let's turn off this line. There. turn off point B. And okay, so here's my cycloid. I'm going to try and find the area under this curve. So we got to remind ourselves, x is equal to t minus sine t, and y is equal to 1 minus cosine t.
Okay.
All right, so let's see. How do we find area under a curve? We integrate. So we integrate y with respect to x, from whatever x value we start at to whatever x value we end at, right? Well, I got the y covered. Y. I got a little problem here. There I have dx.
No, we saw.
Oh,
Wait.
double integration.
Nah, never mind.
Not quite double integration, but I can find dx because I can take the derivative of that.
Yeah.
According to that, dx dt is going to be equal to 1 minus the cosine of t. If I put that derivative in differential form, then that's going to say, do you remember differential forms?
It's going to be dx.
1 minus cosine of t
multiplied
times
by
dt. Yeah. Which I can now substitute in for dx there.
Cool.
So I just want to make a general note about this whole procedure. In general, we're going to have something like x equals f of t and y equals some function g of t. This is going to lead to the fact that dx is going to equal f prime of t dt. That's the differential form in this case. So that means when I take an integral, y dx, and I rewrite it in terms of parameterizations, that's going to give me the integral of y, which is g of t, and instead of dx, I'm going to have f prime of t dt. And usually we change the boundaries of integration from x equals whatever to whatever to t equals whatever to whatever. The bounds of integration are now t's, not x's. Important. And so you really got to slow down when you're doing things in parametric mode because you're not working directly with x anymore, you're working indirectly.
Okay.
So let's see if we can pull this off. So for our particular problem, again, we have x equals t minus sine t, and y equals 1 minus cosine t. And we have our integral y dx becomes the integral, let's see, y is 1 minus cosine of t. And then our dx was, hey, check it out, that was also 1 minus cosine t.
Yes, that's squared.
Oh my gosh.
Oh my gosh, and then it equals the sign. Squared.
So we got to decide, what are our boundaries of integration here?
Sorry, that was so.
We're going to integrate,
Realization there.
Oh, the,
Just tell me to calm down.
They said we didn't write that down.
Oh, and they told me to calm down. Do not tell me to calm down.
Now you need to calm down.
what is t doing to make a complete revolution here? What is t doing to make a complete revolution? What is t to go from here to here?
It's going too high.
It's going from 0 to 2 pi, yeah. So we always need to double check t and x are not the same things. Okay.
in this case?
It just turns out that when x equals 2 pi, y happens to be 0. So it looks like x and t coincide, but they are doing different things.
Okay.
We just happen to have that weird point, 2 pi 0.
Oh my gosh.
Any substitution or should we?
Well, let's see, what do we get? So the observation was made that slow down. No, you have a problem there. If you multiply these guys out,
Doesn't work.
you've got to distribute,
Or we have that.
which is going to give you 1 minus 2 cosine t plus sine squared.
That J.
Wait, if you multiply.
Now, the sine squared's a problem anyway, because how do you find the antiderivative of sine
What?
squared?
How did that happen?
Oh shit, I don't know.
Yeah,
You had to
I
take
don't know
your
where
same
this came
thing.
from.
I'm gonna stop doing that.
Cosine squared plus 1, maybe that's all?
Sorry,
It's like, how can I screw with that?
I was
Sine
thinking ahead.
squared out there.
Maybe. I don't know what happened there. Okay, so looking at this, I can easily take the antiderivative of that. I can easily take the antiderivative of that. I cannot easily take the
Then
antiderivative
you
of that.
fancy dancy integration by parts, right?
Well, I either have to apply something like integration by parts, or I have to apply trigonometric identity to it. Or I look it up in a table of integrals in the book.
I like that one.
Ooh.
I like that idea better.
I
like
I like
it.
that idea.
But I think.
Look it up in your book. I got my book.
For this
Okay,
mathematical
but
reason, if
I
I want to
will
do
do
it
that.
mathematically, I would do the trig identities one.
You can't do use substitution on that?
So with trig identities, I would use let's see what applies here.
Sine one.
The
One plus.
cosine double angle formula.
Yeah, cosine t.
Yeah, so I think the identity I need here is that the cosine of 2 theta is equal to twice the cosine squared of theta minus 1. So if I solve this for cosine squared of theta, then I get cosine squared of theta is equal to the cosine of 2 theta plus 1 all over 2. And I can definitely integrate that without a problem. So, through any means possible, I want you guys to find an antiderivative. I wrote the way I'm going to do it.
Any means possible? You're gonna Wolfram.
Wolfram Alpha is a great means. Yeah, go for it, Zach.
Just we got it. Oh, he's where though. Never mind. Wait, why is it?
He's double.
I'm not done. I'm doing a substitution. All right. So for me then, yeah,
He's not doing the same thing you're doing, Bertie.
I have the integral of 1 minus 2 cosine t plus 1/2 plus 1/2 cosine 2t. I think is what I get, right? Yep. That's what I get. I'm not done yet. I just did my substitution. I got to clean it up a little bit.
Oh.
So that's going to equal, let's see, 1 1/2. I'm going to call that 3/2 t plus 2 sine of t plus 1/4, no, minus 1/4.
Don't worry, you didn't miss a lot.
Oh no, that's wrong. I have a sign error.
I'm just watching it. That's my resource I'm using.
We're not writing it down.
Oh, I'm writing it down. I'm gonna write it down after, you want to make sure you
Oh,
got
I
it right.
forgot because that's on
Yeah, I won't do that.
Okay, so did I do this right? What's the derivative of the sine?
Yes, you're right.
It's the cosine. So every time I do an integration, I take the derivative and make sure I did it right. So that part's right. What's the derivative of sine of 2t? Well, that would be cosine of 2t times 2. And if I take 2 times a fourth, that gives me 1/2. Right? So just something to remember, when you have constant multiples of your variable inside, when you integrate, you divide by them. When you differentiate, you multiply by them. So I think I have the right antiderivative. You do. I'm going from 0 to 2 pi. So here I'm going to go from 0 to 2 pi. Now just a note on that 0 to 2 pi thing. I might observe that this graph is symmetric about the line x equals 3.
It's pi.
Oh, pi, right, shit. Pi. Yes, jinkies. It's
But
pi.
that's almost 3.
So it is almost 3. In Michigan a few years ago, they almost legislated it to be 3.
That's just
I
weird.
know.
Why would they have done that?
Because 3 is easier to work with than pi.
Well,
It
that's
stops.
just reason. No.
So my point is, if I doubled the integral from 0 to pi,
Yeah.
that should give me the whole area
Oh.
due to the symmetry of this graph.
Oh.
Michigan's like, we don't care about that.
Obviously, because
Right, they just,
3.14.
they care about math, they just think 3 is a better number than pi.
Yeah, but 3 and 3.14 are non-negative numbers, which mess you up forever. Like, that's never going to be the same.
So let's figure this out. So what do we get? 3 halves times 2 pi. Sine of 2 pi is 0. Sine of 4 pi is 0. So I'm going to get minus 0 plus 0. And then I get to go minus plugging in 0, which gives me 0 minus 0 plus 0. I love that.
I love it.
What did you find?
No, because it would be sine pi.
Well, I'm plugging in 0 on the lower part.
No, but the last 0 should be sine pi, so.
No, 2, this one right here?
Yeah.
That just gives me 4 pi.
Oh, yeah.
4 pi puts me at the same place as 2 pi. So it's still 0.
Still pi.
I mean, yeah.
Sarah.
Are we okay?
I need to mix up those lines.
So it looks like the answer is 3 pi?
Yeah.
Cool, the area under an arc of a cycloid of radius 1 is 3 pi. Now this is even cooler. I'm just going to back up a step. The general form of a cycloid is r times all this stuff and r times all that stuff. If you change the radius of a circle, you just scale it up or down depending on the size of the circle.
That's cool.
So let's see, what would have happened here? Well, I'd have just a bunch of r's hanging around. So I would have an r from here and an r from there. So there'd be an r squared term hanging around. See where I'm getting that?
Okay, yeah.
Because r is just a constant, right? Constant multiples just get carried along through integration. And so that means the only difference if I change the radius is, in general, it'll be 3 pi r squared. Yeah. So check it out though. What's the area of a circle in general? Yeah, so the area of the cycloid generated by a circle is 3 times the area of the circle.
That's cool.
That is pretty cool, isn't it?
Yeah.
Hey, maybe Michigan was thinking that. Hey, there's 3 times the circle. Choose 3 instead of pi.
I disagree with you.
Yeah.
All right.
Michigan sounds
Plus,
like
that makes pi
80s.
boring.
It does, yeah.
It's just
3
like-
is nearly
oh,
exciting as
it's 3.
3.14, blah, blah, blah.
159. As far as I can go.
We don't.
Then it's like 2, 8.
And that way for like
We don't like.
Okay.
millions of years.
Ready for the next fun part?
Oh, yeah.
Okay.
Never mind that. Ooh, actually, I don't like these as much.
Arc length.
But I can do it.
So I'm going to give you the man on the street's proof of parametric arc length.
Man on the street.
Man on the street. Or gal on the street. I might present this to my mother.
You're too much sometimes.
Okay, so I got this arc here. Do you want to come in and have fun? We're doing arc length.
Oh. Oh, jeez.
Do you have enough of arc length already?
Huh?
You have enough of arc length?
Yeah.
Okay.
Two tests.
That's right. So we're going to zoom way in. You can stay if you share that Rice Krispie treat, though.
No, I'm gonna work out.
Okay, you need that then.
Yep.
Okay,
Yeah.
have fun. All right, so we're zoomed way in on a chunk of arc length. Okay.
Sorry. Okay, well.
It's because Michigan's Christian.
So the more I zoom in on a piece of arc length, the more it's going to look like,
That's not the reason why.
the more it's going to look like kind of a line segment. Okay. Okay. So I'm going to call that DS. DS.
Sounds like a Nintendo.
Yeah, like Nintendo. And then I can make this into a cute little right triangle, where this side of the triangle is dx,
I remember this.
and this one is dy. And so my little chunk of arc length, ds, is related to dx and dy by the Pythagorean theorem.
Oh.
ds squared is approximately equal to dx squared
So learned this.
plus dy squared. Now, in this case, because I have a parameter, my parameter gets to control the size of this triangle. So my dt is controlling the size. So dt starts off as a wicked little number, which makes dx, dy, and ds wicked little numbers. Infinitesimals, we call them. But here's the cool thing I know now. I know then that ds is approximately equal to the square root of dx squared plus dy squared. So that's my little chunk of arc length. And what I really want to do now is I just want to add up all of those ds's. Which means I'm going to add up all of these little Pythagorean chunks. And ultimately, don't I want to take the limit here as dt goes to 0 of my chunks of ds's?
Oh, this is a lot to take in right now.
It's a little messy right there. Let me clean this up. That's slightly neater. That's supposed to be a sigma there.
It's almost like the British pound symbol.
That does a little bit.
Yeah.
Let's fix that up.
Every time you write it. Oh my goodness, does that just dt as the limit as dt goes to
That's
0?
dt is going to 0 there, yeah.
Oh, DT.
Me too.
That happened at neat, right?
That's
It's supposed to be the limit as dt goes to 0. And what happens when I take the limit of a set of sums like this? What do I get? I get an integral.
You get an integral.
Yeah. So it turns out the integral I end up with when I take this limit is the square root of dx dt. I'm going to skip the algebra of that part. Plus dy dt squared dt. That is parametric arc length.
Complicated.
It's pretty much a direct use of the Pythagorean theorem.
Can you multiply
It's
that?
just like a lot to.
It is a lot.
There's a lot to look at there. There's so much going on.
There's a lot going on here. And I skipped a lot of technical steps.
What happens if you multiply that dt and cancel things out? It'll just be dx squared plus dy squared. Square root of that.
Yeah. Yeah, that would basically take you back here.
Because one of these needs to
Yeah. Yeah. So that tweaky little algebraic weirdness allows us to rewrite it as a number. So I skipped the technical steps there, but that's the essence of the formula. That's where it comes from. Which is kind of neat. So we're going to apply that formula to our x equals t minus sine t, and comma y equals 1 minus cosine t.
It's actually it's legal more than
Yeah, it's declared illegal this way.
What was?
Oh.
Oh, good. dx dt equals what? 1 minus cosine t. And dy dt is equal to just the sine of t?
Yep.
Okay. Now, I don't know if you remember this from doing arc lengths back in Calc 2. In general, arc lengths have to be to be doable in a Calc 2 class, you have to choose your function very carefully. Because most arc length problems do not have a fundamental antiderivative. So don't write this down. The original arc length formula you saw in Calc 2 looked like this.
Oh, I'm gonna walk to somewhere. Yeah.
Right? So ours is a variation of that formula. Do you see the relationship?
Yeah, it's been a while. I just
Yeah.
clicked with everything.
So you're taking the derivative, you're squaring it, you're adding 1, and you're putting it in a square root. In general, that makes a mess. And you're not going to be able to find the antiderivative. So let's see if we get lucky.
What do we do?
You think we're going to get lucky?
Yeah, I see.
All right. Back season.
Oh, no, I can't. No.
Okay. So what we're going to have is we're going to have to square these guys, right? So I'm going to have 1 minus the cosine of t squared. I'm going to have to add that to the square of dy, t, a little easier. And all that fits inside the square root. And I'm integrating, in this case, from 0 to 2 pi. And we've seen some of this, right? Let's do this a little bit more. So let's see, if I multiply that out, I'm not going to redo the whole integral, I'm just going to rewrite this part. That's going to give me 1, I guess it'll be parentheses now. That's going to give me 1 minus 2 cosine of t plus cosine squared of t. Hey, but I also have plus a sine squared of t hanging out there with it, don't I?
Yeah.
And why do we love these guys together?
Because they make 1.
Because they make 1.
Yay! Yay!
Combine that with this one here. So now I have the integral from 0 to 2 pi of the square root of 2 minus 2 cosine of t.
Back up to.
Could factor out the 2. So that's going to give me, so I'm just going to pull that completely out. Sorry, I have too much chocolate.
Ah, see?
Zach spurred me along and not taking notes. Just taking notes. Thank you, Sean.
I'm
Jeff is
terrible.
not taking notes.
Obviously chocolate
Yes.
works.
Wait, chocolate worked for two.
You.
Oh my gosh.
Didn't have any chocolate.
Well, maybe the
Just the-
idea of having it here.
That I asked nice.
Having chocolate would have been bad.
Said I wouldn't give him a shot collar if he didn't use. Okay, we had a problem. I forgot my DT. That's not my problem though. I have a bigger problem than that. Off the top of my head, I don't know any derivative. Wait a minute. I got an idea. I used a substitution earlier, trig identity. I have a feeling that identity might work here. Let's see.
I feel like you're acting.
A little bit. Not so good. How bad acting. Okay. So,
We all have our.
all right. So let me think. We
I'm trying
used
to
the.
inform you guys.
Let's see. I had the cosine of 2 theta equals twice cosine squared of theta minus 1. The alternative formula there is 1 minus twice the sine squared of theta. And if you solve that for sine squared of theta, you get what's called the half angle formula. Okay, so I'm just going to do that. I'm going to add, subtract the 1 to the other side.
Yeah.
So I'm using this combination right here. So that's going to give me cosine of 2 theta minus 1 equals negative 2 sine squared of theta. So I subtracted 1 over. I'm going to divide by negative 2. So here I've divided by negative 2. Which I could do a little jiggery-pokery on that. Dividing by 2 is the same as multiplying by a half, right? So I'm going to pull out a half. Oops. And then I'm going to take the negative to switch the signs of these guys. So that's going to give me 1 minus cosine of 2 theta. And that is equal to the sine squared of theta. Guess what I'm going to do next? Exactly. Yeah, I'm going to take the square root also. So I'm going to rewrite with the square root, so square root of that, square root of that. So then what I get is I get the square root of 1/2 chilling out front. Then I have the square root of 1 minus, or the cosine of 2 theta. But Zach had an excellent point. He said, why don't we replace 2 theta with t?
Oh, substitution.
Substitution. What if we replace...
That's what I was wondering about.
Yeah.
Because I was like, well, where's the t?
Yeah, so what if we replace 2 theta with t? What's theta have to be?
1
t over 2. Yeah,
T over 2.
yeah, and that's going to cancel pretty much, leaving the sine of t over 2. So let's see. I have this square root on the other side in my integral. So I'm just going to multiply both sides by the square root of 2. That'll cancel this. And so there's my substitution. I made that. I probably made that harder than it was, but I was just messing around. Okay, so let's see if we can put that back in. What's that?
That's a half angle formula up there.
So I took the double angle formula and I changed it to a version of the half angle formula.
A version.
Yeah, so the half angle formula usually looks like this.
Yeah,
The
that's
sine of t over 2
Yeah.
is equal to the square root of 1 minus the cosine of t all over 2.
So why don't you just use that?
Because I can never remember that, but for some reason I always remember the cosine double angle formula, and then I solve.
Is the other one easier? Here?
I don't think so.
So
It
you
depends
just
on the
have to
individual. You think the
divide
other one's
by
easier to
two.
use?
So that ended being.
Your call. So, we're using that formula right there.
I have like a table in my notes, and I
Half
always
angle
look at them.
Either one. They both work.
Should that end up being 2 sine t over 2? Is there had a root 2 pulled out? That integral?
You mean back here?
No, go back again.
Right here?
Still up there. Well, you were, yeah,
I
I
couldn't-
put it all down. It was 2 minus 2 cosine t. They pulled the root 2 out, put it on the other side of the integral, so it ends up being.
Here?
You need to go back to another page.
Another page. Here? Okay, so I got this one right here.
Yeah, that square root
That's
2.
where we left off.
That's just what.
Yeah, but then you need that 1 over square root of 2 that you added the cosine for that half.
Right, yeah, so what I'm saying is the square root of 1 minus cosine of t is equal to square root of 2 times the sine of t over 2. Which we can get from this formula too, because this just means 1 minus cosine of t in the square root divided by the square root of 2. I really only want that part, so I have to put the square root of 2 on the other side. Okay, so then my new integral, so I had the square root of 2 times the integral of the square root of 1 minus the cosine of t dt. Based on my substitution, that is now this inside of the integral is square root of 2 times the sine of t over 2.
Oh, you haven't integrated yet. Okay.
No, I haven't integrated yet. So putting the constants together gives me a 2. Antiderivative for the sine is a cosine. Now, the chain rule here says going the other direction, you would have to multiply by a half. So going in this direction, I'm going to divide by a half or multiply by 2. That's going to throw another 2 in there. Just to double check that's true, if I take the derivative of the cosine, so the derivative with respect to t of the cosine of t over 2 is equal to the derivative of cosine, ooh, I got another problem.
Negative.
This negative sign, and then I have to multiply by a half. So that's why I put the 2 in front, and now I have to make it negative also. That looks like, let's fix that. So it's a negative 2 cosine of t over 2. All right, let's pull this junk out of here. Ah, I missed. Got it. Bye-bye. All right, so we're going to integrate that from 0 to 2 pi. So what's that going to give us? 2 times cosine of pi is -1, so I'm going to have -2 times -1. Cosine of
Maybe
0.
Pull out the -2 and then.
Oh, you could, yeah, you could do it that way too. I'm going to leave it in. I'm going to have minus -2 times the cosine of 0,
So it's 0.
which is 1. Now, cosine of 0 is 1. All right, so cleaning up the signs, I have positive, positive. 2 plus 2 is 4. 4 times 2 is,
4 times 2?
oh yeah, 2 plus 2 is 8. 2 plus 2 is 4 times 2 is 8. This equals 8.
If you're gonna multiply in that minus, shouldn't it be -1 also? 2 times -1?
How's that? Oh. I was
Come
gonna say.
on.
No, here's my -2. Right?
So you got -2 and -1.
Cosine of 0 is 1.
Right.
Cosine of pi is -1. So -2 times -1 is 2.
Yeah.
And then I'm minusing -2, which is really a plus 2. Times the 2 out front is 8.
But if you're gonna multiply that -2 and make the positive, should that 1 also become negative?
I'm not multiplying negative through.
Oh.
Write it down.
Oh, okay.
Yeah,
that's good.
great.
Write it down, Zoc.
I'm an idiot.
I got what you got,
I'm
Gary.
sorry.
Now, it's easy to screw up signs, and there's no best way to deal with it. It depends on the person, the time of day.
Yeah.
So, this is kind of cool.
Okay.
Person.
The arc length, oops, wrong button.
All of that confusion brought us to an 8.
Where the hell did it go? Come on, baby, where are you? There you are. The arc length of rolling that circle and watching that point, if the circle rolls once, it covers a distance of 8 units. Along the ground, 6.28 roughly. In the air, it covered 8 units. Now, what if we throw an arbitrary radius in there? What's going to happen? So what if we throw an arbitrary radius in there? Well, let's take a look. So, let's see, that's not it. Okay, arc length, we're getting there. Right here. So that means I would have r times this stuff, and I would have r times that stuff, right? Well, in my derivatives, well, the r is still getting carried along for y. Still getting carried along here. So that means here I will have an r squared, because it's the derivative squared. Here I will have another r squared. And we can pull out that common factor, right? What's the square root of r squared? R just gets carried along. Constant multiple. So in general, if we roll a circle of radius r, the arc length would be 8r. Okay. Unfortunately, we are out of time to revolve that around an axis and see what happens. It was probably for the best. That was pretty dang intense.
Yeah.
Okay. So you guys need to take your power series test sometime this week. It'll be shorter than the test you already took.
How many problems exactly?
Somewhere between 5 and 10.
Just, oh,
Well, each
wait,
one
what?
has 12 letters.
No, they do not. I promise. Each one is 1 point.
Have you written the test yet, or are you giving us like each different test?
I've written the test.
Okay, but between 5 and 10.
Between
So
5 and 10.
how long do you think it'll take us? That's really what I would like.
I'm hoping you can do it in 45 minutes.
No.
Okay, the last test was too long. I agree. It needs to be short.
Oh, what's that?
All right. So,
Oh.
what have we covered in class?
A lot of stuff.
We have covered section 11.1.
Don't say 11-2. Don't say
11.1 is just the algebra of parameterizations.
11-2.
And 11.2, Paisley, is the calculus of parameterizations.
It's okay. It's okay.
And there's only about 10 problems for each one. I didn't sign
Oh,
much.
that's really nice.
Thank you.
They're
But I
really
would recommend
hard.
doing some of the cute ones in the book. I'll point them out in class on Thursday.
Cute. They're cute.
I look for these cute ones, and I never find them.
I can find them, probably.
The Witch of Agnesy, that's a good one.
What?
There's a problem in the book called The Witch of Agnesy.
Oh, I thought you said something else.
Yes. Exactly.
So we're going to review this stuff on Thursday, and on Thursday we're going to start 11.3, which is on cute polar stuff.
Yay!
Matt, you are just overly enthusiastic about the class.
Me?
Yeah.
Well, it's one of my favorite classes,
So cute polar stuff on Thursday. Polar stuff is awesome. We're gonna draw flowers with calculus. We're gonna find the area inside of things.
It really does.
All right. That's it for now. Ta-ta.
Go get it.